Hello, and welcome to the Whispered Lore. As the quiet of the evening settles around you, allow your thoughts to soften and your breathing to deepen. Tonight, we journey back in time, not to the clash of legions, but to the steady, life-giving pulse of an empire. We turn our attention to one of its greatest, most serene achievements, the Roman aqueducts. In our exploration of Flow of an Empire, we will gently trace the paths of these masterful structures, considering the quiet ingenuity of their engineering and the constant, dedicated maintenance they required. There is no need to focus too intently. Simply rest, and let the story of flowing water carry you toward a peaceful slumber. The sound of water is the sound of life. A gentle lapping against a riverbank, the steady patter of rain filling a cistern, the satisfying gurgle of a spring emerging from the earth. For the earliest inhabitants of the Seven Hills, these were the sounds that defined their existence. The city of Rome, destined to become the heart of a vast empire, was born beside a river, the Tiber. This sinuous, often unpredictable waterway was the city's first and most essential artery. It provided water for drinking and for cooking. Its currents carried away waste. Its banks irrigated the small agricultural plots that fed the city's nascent population. Alongside the Tiber, a network of local springs, such as the sacred spring of Juturna in the Forum, and a multitude of hand-dug wells, provided supplemental sources. In the modest homes of the early Republic, rainwater was dutifully collected, channeled from the roof through an opening known as the compluvium, and gathered in a shallow basin below, the impluvium, before being stored in an underground cistern. For centuries, this patchwork system of local sources was sufficient. The city was a compact entity, its population manageable, its needs modest. The Tiber, the springs, the wells, and the rain, in their aggregate, quenched the thirst of early Rome. But the city did not remain modest. As the Republic expanded its influence, first across the Italian peninsula and then beyond, Rome itself underwent a profound and inexorable transformation. Its population swelled. What had been a town of tens of thousands grew into a metropolis of hundreds of thousands, and eventually, by the dawn of the imperial age, it was approaching a population of 1 million souls. This demographic explosion placed an unsustainable pressure upon the city's ancestral water sources. The Tiber, which had once been a source of life, increasingly became a receptacle for death and refuse. The city's great sewer, the Cloaca Maxima, originally an open-air canal designed to drain the marshy lowlands of the Forum, now discharged a constant, foul stream of human and animal waste directly into the river, often upstream from the very areas where citizens drew their water. The river's water became turbid, unsafe, and a vector for disease. The local springs, while often of excellent quality, were limited in their output. They could not scale to meet the demands of a population that was growing exponentially. Wells, too, were problematic. They were susceptible to contamination from surface runoff and primitive sanitation, and their levels could fall dangerously low during the dry Mediterranean summers. The rainwater cisterns of private homes, while useful, were entirely dependent on seasonal precipitation, and could not possibly serve the needs of the burgeoning number of landless plebeians crowded into multi-story apartment blocks or insulae. The Rome of the late 4th century BC was a city straining at its environmental limits. It was a city that was, quite literally, thirsty. The need was not merely for potable water to drink, but for water to sustain the very fabric of an urban civilization. Water was needed for cleaning the increasingly crowded and unsanitary streets, for the operation of workshops and industries such as fulling and dyeing, and for the basic hygiene that prevents the outbreak of plagues. The traditional, localized water solutions were failing. A new paradigm was required, a solution as bold and ambitious as the burgeoning republic itself. The Romans, practical and methodical, began to look beyond the immediate vicinity of their city walls. Their gaze fell upon the distant hills, the Alban Hills to the southeast, and the Sabine Hills to the east, where pure, cold springs flowed in abundance, fed by the Apennine watershed. The monumental arch, the graceful silhouette against a Mediterranean sky, is the enduring image of the Roman aqueduct. It is a symbol of power, of engineering prowess, and of an empire's ability to bend nature to its will. But this image, while iconic, is an incomplete one. It represents the culmination of a long and methodical evolution, a journey that began not with grand arches, but with the most fundamental and localized of solutions. Before water could flow for miles across valleys, it first had to be drawn from the earth, collected from the sky, and channeled through simple, hidden conduits. This is the story of those precursors, the humble and essential waterworks of early Rome. In its nascent stages, as a small collection of settlements upon the Seven Hills, Rome's relationship with water was immediate and intimate. The city's very lifeblood was the river that coiled through its landscape, the Tiber. For the early Romans, the Tiber was the primary and all-encompassing source. It was from its murky, swirling currents that water was drawn for drinking, for cooking, for washing, and for the irrigation of small agricultural plots. The river also served as the city's first and most efficient sewer, carrying away the waste of a growing populace. But reliance on the Tiber was fraught with inherent difficulties. Its water was often turbid, carrying silt and organic matter. It was subject to the whims of the seasons, prone to devastating floods in the spring and shrinking to lower, more sluggish levels in the dry summer months. Furthermore, as the city grew, the water downstream became progressively more polluted, a repository for refuse and runoff. And in times of conflict, a single exposed water source was a point of extreme vulnerability. To supplement the river, the early inhabitants turned to more localized sources. Springs, seeping from the porous tufa rock of the hills, were particularly valued. These were seen not merely as sources of water, but as sacred places, often associated with deities and nymphs. The spring of Juturna in the Roman Forum, for instance, was a vital and revered source for centuries, its water considered to be of exceptional quality. Yet, springs were finite. Their flow was limited and could not possibly sustain a burgeoning urban center. Thus, the Romans developed a more private and decentralized solution, the well, or puteus. This was a simple vertical shaft, excavated by hand down to the water table. The geology of the Roman hills, composed largely of soft volcanic tufa, made such excavation relatively straightforward. Early wells were often simple, unlined pits. Over time, however, construction became more sophisticated. To prevent collapse, the shafts were lined. Some were reinforced with a framework of timber. More permanent wells were lined with rings of terracotta, stacked one upon the other, or, in the most robust examples, with carefully cut blocks of stone, a technique known as opus quadratum. Water was drawn by hand, with a simple bucket and rope, a laborious but reliable method for an individual household. The well represented a crucial step towards water independence, freeing a family from the daily trek to the river or a public spring. Alongside the exploitation of groundwater came the systematic harvesting of rainwater. This practice, likely refined through contact with Etruscan and Greek cultures, became a defining feature of Roman domestic architecture. The typical Roman house, the domus, was designed around an open courtyard, the atrium. The roof of the atrium sloped inwards towards a rectangular opening called the compluvium. Directly beneath this opening, set into the floor of the atrium, was a shallow basin, the impluvium. Rain falling on the roof was channeled through the compluvium and collected in the impluvium. This system was an elegant and efficient means of capturing a clean, reliable source of water. The water from the impluvium, however, was not left to stagnate. The great aqueducts, those monumental assertions of Roman will upon the landscape, did not begin with the quarrying of stone or the mixing of mortar. They began, as all such undertakings must, with a thought, an idea, and then a measurement. This is the story of that initial intellectual phase, the surveying of the land, which takes place within the mind of the architect, the architectus, long before the first shovel breaks the earth. The fundamental principle is, of course, deceptively simple. Water flows downhill. But to harness this principle over dozens, sometimes hundreds of kilometers across a landscape of hills, valleys, and plains requires a mastery of geometry, an intimate understanding of topography, and an almost obsessive attention to detail. The central challenge was not merely to make water flow, but to control its descent with unwavering precision. The ideal gradient for a Roman aqueduct was remarkably slight. A fall of only a few meters over a kilometer was not uncommon. Too steep a gradient, and the rushing water would scour and erode the carefully constructed channel, its abrasive force wearing away the waterproof lining and even the stone itself over decades of constant flow. Too shallow a gradient, and the water would become sluggish, stagnant, allowing sediment to settle and impurities to accumulate, choking the channel and fouling the supply. The flow had to be constant, gentle, and persistent, a managed, civilized flow, not a wild torrent. The process began at the source, the Cappadocian. The selection of a spring or river was a matter of considerable study. The architect would assess not only the volume and reliability of the water source throughout the year, but also its purity. Vitruvius, the great chronicler of Roman engineering, advises on methods for this determination. One should observe the physical condition of the local inhabitants who drink from the source. Are they robust and healthy? One could also inspect the livers of local animals. A healthy, untainted liver suggested pure water. The clarity, taste, and temperature of the water were all considered. Once a suitable source was identified, the true work of the surveyor, the grammaticus or librator, could commence. Their toolkit was simple, yet in skilled hands extraordinarily effective. For establishing straight lines and right angles, essential for plotting the course and laying out construction sites, they employed the Groma. This instrument consisted of a vertical staff, upon which was mounted a horizontal cross. From the end of each of the four arms of this cross, a plumb line or perpendiculum was suspended. By sighting along two opposing plumb lines, the surveyor could establish a perfectly straight line of sight. By then sighting along the other pair, a line at a perfect 90-degree angle could be laid out. The Groma was an instrument of alignment, not of leveling. Its purpose was to project the intended path across the land, marking the route with a series of stakes, or pali. The critical task of determining the gradient fell to a different instrument, the chorobates. This was the Roman engineer's spirit level, writ large. It was a long, sturdy plank of wood, perhaps 6 meters in length, supported by 2 legs at either end. These legs were braced to the main beam. On the top surface of the beam, a long, narrow channel was carved. In practice, the surveyors would set the chorobates in place and fill this channel with water. If the water level was consistent with the edges of the channel along its entire length, the instrument was perfectly level. This method was far more reliable than an alternative system that used plumb lines hanging from the top beam against markings on the braces, as the slightest breeze could disturb the plumb bobs and produce a false reading. The hydrostatic principle of water finding its own level was an incorruptible referee. The process of surveying with the chorobates was painstaking. The continuous, gentle decline of the aqueduct channel, the spicis, was the singular, non-negotiable principle of its design. For water to flow, it must move from a higher point to a lower one, guided by nothing more than the persistent and subtle force of gravity. While the vast majority of an aqueduct's length was discreetly hidden beneath the earth's surface, traversing the landscape through subterranean channels, there were inevitable moments where the unwavering, gravity-defying gradient encountered a significant depression, a valley or a river plain, which necessitated a more dramatic and visible solution. It was in these topographical challenges that Roman engineering found its most iconic expression, the elevated superstructure, the aqueduct bridge. These were not built for aesthetic grandeur, though they achieved it, but out of absolute necessity. They were the most expensive, labor-intensive, and structurally complex sections of any aqueduct line, and their construction represents a masterful synthesis of material science, structural mechanics, and logistical organization. The fundamental element that made these colossal structures possible was the semicircular, or Roman, arch. The principle is one of elegant efficiency. Stone, the primary building material, possesses immense compressive strength but is notoriously weak under tension. A simple horizontal beam, or lintel, spanning a wide gap will sag under its own weight and the load above it. The bottom surface of the beam is stretched, placed under tension, and is therefore liable to crack and fail. The arch, however, brilliantly converts the downward vertical force of the load into a diagonal, outward and downward thrust. This force is channeled through the individual, wedge-shaped stones of the arch, known as voussoirs. Each voussoir is in a state of constant compression, pressing tightly against its neighbors. The force follows the curve of the arch down to its springing points, the imposts, and is then transferred vertically down through the massive supporting piers and into the foundations. The final, central voussoir placed at the apex of the arch is the keystone. Its placement locks the entire assembly into a state of static equilibrium, making the structure self-supporting and incredibly strong. The construction of such a sequence of arches began, as all Roman engineering projects did, with meticulous surveying and the laying of foundations. The surveyor, using instruments like the corrugates, a long wooden plank with a water level, would establish the precise location and elevation for each pier. The stability of the entire superstructure depended entirely on the integrity of its foundations. In firm, stable ground, workers would excavate deep trenches, often down to bedrock, which would be filled with a solid mass of Roman concrete, or opus caementicium. This material was a revolution in itself. A composite of lime mortar, water, and an aggregate, typically broken stones, which we call caementa. When the aggregate included a specific volcanic ash known as pozzolana, found in abundance near the Bay of Naples, the concrete gained remarkable hydraulic properties, meaning it could set and harden even underwater. For piers that had to be built in the middle of a river, Roman engineers would first construct a cofferdam, a temporary watertight enclosure, pump the water out, and then pour the pozzolanic concrete foundation directly onto the riverbed. Upon these unyielding foundations, the piers would begin to rise. The most durable and prestigious structures were built using dimension stone masonry, or opus quadratum. Large rectangular blocks of travertine or tufa were quarried with precision, transported to the site, and then lifted into place using complex cranes powered by human treadwheels. Each block was dressed to fit its neighbors perfectly, often with such precision that no mortar was needed in the joints. While the image that persists in the collective imagination is one of towering arcades marching across the sun-drenched Campagna, this vision, though magnificent, represents but a fraction of the Roman aqueduct system. The true and overwhelmingly larger component of this vast hydraulic network lay hidden from view, a silent, subterranean servant buried within the earth. It is in the methodical construction of tunnels and trenches that we find the pragmatic core of Roman water engineering. This was the unseen majority, constituting, by most estimates, over 80% of the total length of any given aqueduct. The decision to place the water channel, or specus, underground was not born of modesty, but of profound practicality. A subterranean conduit was shielded from the elements. The water remained cool, free from the evaporation caused by the Mediterranean sun. It was protected from accidental or deliberate contamination by animals, falling leaves, or human activity. In times of conflict, an underground channel was infinitely more secure from sabotage than a vulnerable, exposed structure. Most importantly, however, following a subterranean path allowed the Roman engineers, the liberatores, to maintain the precise, shallow gradient required for the steady, continuous flow of water. It was far more efficient in terms of labor and materials to dig down into the earth than to build up over every minor undulation of the landscape. The most common method for creating these underground channels was the technique known as cut and cover. The process began, as all Roman engineering projects did, with meticulous surveying. Using instruments like the corrugates, a long wooden plank with a water level, and the groma for laying out right angles, the surveyors would plot the aqueduct's course with painstaking accuracy. Once the path was staked, legions of workers would begin the excavation. A long, deep trench was dug, its dimensions carefully calculated to accommodate the conduit and the laborers who would build it. Within the open trench, the specus itself was constructed. The foundation, or solum, was typically a bed of compacted earth and rammed rubble, providing a stable base. Upon this, the walls of the channel of the parietes were raised. These could be fashioned from dressed stone blocks, known as opus quadratum, or more frequently, from the Romans, signature material, concrete, or opus caementitium. Often, this concrete core was faced with brick, a style called opus testaceum, creating a durable and regular surface. The interior dimensions of the channel were not arbitrary. They were tailored to the expected volume of water, ranging from less than a meter in width and height for smaller lines to channels large enough for a person to walk through. The most critical element of the conduit's construction was its lining. To ensure the channel was completely watertight and to prevent the lime in the mortar from leaching into the drinking supply, the Romans applied a specialized waterproof plaster called opus signinum. This was a remarkable substance, a form of hydraulic mortar made by mixing lime, sand, and crucially, crushed terracotta pottery or tiles. This aggregate of crushed ceramics, pozzolanic in nature, reacted with the lime to create a hard, impermeable surface. Laborers would apply the opus signinum in multiple layers to the interior walls and floor of the specus, troweling it to a smooth, dense finish. The result was a distinctive, reddish-pink lining that sealed every joint and fissure, minimizing water loss over distances that could span many kilometers. Once the lining had cured, the channel was covered. This could be achieved with simple, flat stone slabs laid across the top of the walls. More commonly, especially for larger channels, a vaulted, arched roof of stone or concrete was constructed. The journey of water from a distant, pristine source to the heart of a bustling Roman metropolis was not a simple act of diversion. It was a complex, meticulously planned process, a symphony of observation, surveying, and construction, governed by the unyielding laws of physics. The process began not with grand construction, but with the quiet, methodical art of observation, a discipline predicated on understanding the subtle language of the landscape. The Roman water engineer, or aqueducts, would seek out potential sources, primarily springs or fontes, and sometimes rivers or lakes. The selection was paramount. The ideal source was high in elevation, copious in its flow, and, above all, pure. Vitruvius, in his seminal work De Architectura, outlines the methods for assessing water quality. One primary technique was empirical, involving the observation of the local inhabitants who drank from the source. Their physical condition, their complexion, and their general state of health were considered direct indicators of the water's wholesomeness. For a more direct, almost clinical analysis, the Romans would examine the livers of animals that grazed in the area and drank from the water. A healthy, untainted liver suggested the water was safe for human consumption. More prosaic tests were also employed. A sample of the water would be boiled in a bronze vessel. If no sediment remained after the water had evaporated, and the vessel itself was left unstained, the water was deemed pure. Its clarity and lack of odor or taste were, of course, fundamental prerequisites. Once a suitable source was identified and its quality confirmed, the first structure was erected, the spring house, or caput aquae. This was a collecting basin, often a small, enclosed stone structure built directly over the spring's egress point. Its function was twofold: to gather the water into a single, manageable channel and to protect it from contamination by surface runoff, falling leaves, or animals. This initial basin acted as the formal beginning of the aqueduct proper. From this point, the water began its long, gravity-powered descent. The single most critical principle of Roman aqueduct design was the maintenance of a consistent, shallow gradient. This was not a rushing, turbulent flow, but a slow, placid, and continuous movement. The gradient was astonishingly slight, often as little as 1 part in 3,000, or a drop of roughly 30 centimeters for every kilometer traveled. This imperceptible slope was calculated with remarkable precision using instruments such as the corrugates, a long wooden plank with a water level, and the Groma, a surveying tool for laying out right angles. Maintaining this gradient over dozens of kilometers of varied terrain was the central engineering challenge. The primary conduit, the specus, was a testament to the Roman preference for the subterranean. Over 80% of the total length of most aqueducts ran underground, either in tunnels bored through hills, or, more commonly, in trenches dug and then covered over. This cut-and-cover method was practical and effective. It protected the water from evaporation and contamination, kept its temperature cool and stable, and concealed this vital lifeline from potential enemies. The specus itself was typically rectangular, about 1 meter wide and 2 meters high, allowing access for maintenance. Its walls were constructed from cut stone, brick, or the Romans' revolutionary material, opus cementicum, a form of concrete. To ensure the channel was completely watertight, the interior was lined with a distinctive reddish mortar known as opus signinum. This was a composite of hydraulic lime, pozzolanic ash, sand, and crucially, crushed fragments of terracotta tiles and pottery. The great aqueduct channels, having traversed miles of countryside, across valleys and through mountains, have now reached the perimeter of Rome. Their journey, a monumental statement of engineering prowess, is largely complete. But here, at the city's edge, a new, more intricate, and less celebrated phase of water management begins. The water has arrived, but it has not yet been delivered. This is the story of its final, carefully controlled dispersal into the urban fabric, a process that dictates the rhythm of daily life within the capital. Upon entering the city, the water from a specific aqueduct did not simply flow freely into the streets. Instead, it was directed into a primary distribution basin, a large, covered tank known as a castellum aquae, or water castle. These were not merely reservoirs. They were sophisticated pieces of hydraulic engineering. Often architecturally impressive, their primary function was to reduce the velocity of the incoming water, allow any remaining sediment to settle, and serve as the central node from which the city's water supply was methodically apportioned. Inside the castellum, the environment was dark and cool. The water would enter, its powerful flow from the main channel dissipating in the larger volume of the tank. Here, a system of sluice gates, operated by bronze or iron mechanisms, controlled the outflow. The first principle of distribution was gravity. The height of the castellum aquae relative to the surrounding city districts was of paramount importance. A higher elevation provided greater water pressure or head, allowing for more forceful delivery to fountains and upper floors of buildings. Consequently, the terminal castella for aqueducts, like the Aqua Marcia, sourced from high elevations, were strategically placed on some of Rome's highest hills, such as the Esquiline. From this main castellum, the water was divided. The great water administrator, Sextus Julius Frontinus, writing in the late 1st century A.D., provides an invaluable account of this system. He explains that the water was typically channeled into 3 main categories of use, often through a trio of separate outlets positioned at different heights within the castellum. This stratification was a deliberate safety measure. The lowest outlet, which would be the last to run dry if the supply faltered, was dedicated to the public fountains, or lacos. This ensured that the general populace, the vast majority of whom relied on these fountains for their daily water needs, would have access for as long as possible. The water for drinking, cooking, and washing was considered a non-negotiable public provision. The outlets set at a higher level in the castellum wall fed the great public baths, the thermae. These magnificent complexes were prodigious consumers of water, requiring a constant, voluminous supply to fill their various pools, from the hot caldarium to the cold frigidarium. Because the baths were a public service, but one of amenity rather than pure necessity, their supply was prioritized below that of the public fountains. The highest outlets were reserved for private customers. These were wealthy individuals, workshops, or businesses that had been granted the right to a direct water connection by imperial decree. This was a rare and expensive privilege, a beneficium granted by the emperor, and its supply was the first to be cut off in times of drought or if the aqueduct required repairs. Water, in its purest, most accessible form, was a symbol of status. From the main Castellum Aquae, the water destined for different city regions was funneled into a network of smaller, secondary castella, which further subdivided the flow. It was from these local distribution points that the final delivery network radiated outwards. This network consisted of an immense and complex web of pipes laid beneath the streets and sidewalks. The primary conduits were typically made of lead, known as fistulae plumbae. The great stone arches, striding across the landscape, are but the most visible testament to Roman hydrological genius. They are monuments to an initial, monumental effort, but a monument, once built, can be left to the elements. An aqueduct cannot. An aqueduct is a living system, a conduit for the lifeblood of a city, and like any living system, it requires constant, unceasing care. This was the domain of the Curator Aquarum, the curatorship of the waters, a complex and highly organized bureaucracy dedicated to the perpetual task of maintenance. The story of the aqueducts is not merely one of construction, but one of endless preservation. The system was overseen by an official of the highest rank, the Curator Aquarum. This was not a minor municipal post. It was a prestigious position, often held by a former consul, a man who had already reached the pinnacle of a Roman political career. The gravity of the appointment underscored the absolute centrality of the water supply to the functioning of Rome. We know of this role in intimate detail thanks to one of its most famous holders, Sextus Julius Frontinus, who around the year 97 AD penned a comprehensive report titled De Aqueductu Urbis Romae, or On the Water Management of the City of Rome. His work provides an unparalleled window into the challenges and procedures of aqueduct maintenance. Frontinus describes a vast and specialized workforce under his command. These were the aquarii, the watermen. This corps was divided into two primary groups: the Familia Aquaria Publica, a state-owned contingent of slaves numbering around 240, and the Familia Aquaria Caesaris, an even larger imperial contingent of 460, established by the Emperor Claudius. These 700 men formed the permanent, professional army against the forces of decay. Their duties were varied and meticulously delineated. The most fundamental task was inspection. Teams of circutores, or inspectors, would patrol the entire length of their assigned aqueduct. They walked the service roads that ran parallel to the channels, their eyes trained on the stone and masonry. They looked for the telltale signs of trouble, a dark patch on the stone indicating a slow leak, the aggressive encroachment of tree roots threatening the foundation, or cracks in the structure, however minute, that could widen with the seasonal freeze and thaw. They would listen for changes in the sound of the water, a subtle indicator of an obstruction or a change in flow rate. The most insidious and persistent enemy was internal, the slow, silent accretion of calcium carbonate. The water that flowed from the springs in the Apennine Mountains was exceptionally hard, rich in dissolved minerals. As this water traveled through the relatively smooth, dark channel of the aqueduct, known as the specus, these minerals would gradually precipitate out of the solution, forming a hard, rock-like scale on the interior surfaces. This deposit, or center, would build up layer by layer, year after year, like rings on a tree. Left unchecked, it could reduce the cross-section of the channel by a significant margin, sometimes by more than half, severely constricting the flow of water and diminishing the aqueduct's discharge capacity. Dealing with this center was a brutal, thankless task. To remove it, a section of the aqueduct had to be temporarily decommissioned. This required sophisticated water management. Sluice gates at upstream junctions would be closed, and the water diverted into a parallel channel or simply allowed to discharge into a nearby river, a carefully calculated loss. Once the specus was drained, the aquarii would descend into the channel through access shafts, or puttae, which were spaced at regular intervals along the underground portions of the line. In the cramped, damp darkness, illuminated only by oil lamps, they would set to work with hammers and chisels. While the aqueducts of the city of Rome represent the apex of hydraulic engineering in the ancient world, their fame often obscures a more fundamental truth. The aqueduct was not merely a metropolitan luxury. It was a standardized instrument of Romanization, an essential component of the provincial urban kit, deployed from the misty frontiers of Britannia to the sun-scorched landscapes of North Africa. The delivery of a consistent, copious supply of fresh water was the prerequisite for the Roman way of life. It fed the great bath complexes, the thermae, which were social and business centers. It supplied the public fountains, or nymphia, that were points of civic pride. And it flushed the latrines and sewers that made high-density urban living tenable. To build an aqueduct in a newly conquered or colonized territory was to stamp the indelible mark of Rome upon the land, to transform a settlement into a city. In Gaul, the structure that most immediately commands attention is the Pont du Gard, a segment of the aqueduct of Nemausus, modern-day Nimes. Constructed in the middle of the 1st century A.D., this aqueduct was a work of profound precision. Its source was a spring near Uzes, and its destination was the Castellum Aquae, or distribution tank, in Nimes, a journey of approximately 50 kilometers. The most remarkable characteristic of this system is its gradient. Over its entire length, the channel descends a mere 17 meters, an average gradient of only 1 in 3,000. This demanded an extraordinary level of skill from the Roman surveyors, the mensors, who would have used instruments such as the corybates, a long wooden plank with a water level, to maintain this minimal yet constant slope. The Pont du Gard itself, spanning the Garden River, is but a small fraction of the total length, yet it is its most architecturally dramatic. Composed of 3 tiers of arches, it reaches a height of 49 meters. The primary construction material is a local, coarse-grained yellow limestone, quarried in the immediate vicinity of the structure. The largest blocks of the lower tiers, some weighing up to 6 tons, were laid without mortar, a technique known as opus quadratum. The precision of the stonework, with blocks cut to fit perfectly, ensured the stability of the immense structure through compressive force alone. The water channel, or specus, which rests atop the 3rd tier, is a rectangular conduit approximately 1.8 meters high and 1.2 meters wide, constructed of mortared rubble and lined with a waterproof cement of lime, sand, and crushed terracotta, known as opus signinum. This reddish plaster prevented leaks and kept the water pure. Moving to the Iberian Peninsula, to Hispania, the aqueduct of Segovia stands as a monument to sheer, unadorned structural honesty. Likely completed under the reign of Trajan in the early 2nd century A.D., it is a testament to the practical application of gravity and friction. It transported water from the Frio River in the mountains, 16 kilometers distant from the city. As it approaches Segovia, the terrain dips into a valley, and here the aqueduct rises to its most impressive form. A 2-tiered arcade of 167 arches, built from over 24,000 massive, rough-hewn granite blocks. Like the Pont du Gard, these blocks were set without any mortar or clamps. The stability of the structure, which at its highest point reaches over 28 meters, is a function of the careful balancing of forces, a static equilibrium achieved through the immense weight and precise placement of each individual stone. Close inspection reveals that the blocks are not perfectly uniform. They are dressed on the sides that meet other blocks, but often left rough on the exterior faces. This suggests a focus on function over fine ornamentation, a hallmark of Roman military engineering. The flow of an empire is not unlike the flow of its water. For centuries, the aqueducts were a testament to permanence, a system so vast and so robust as to seem an elemental part of the landscape, as fixed as the hills and the rivers they tamed. Yet, like all complex systems, they were exquisitely vulnerable. Their existence depended not merely on the soundness of their initial construction, but on a constant, unbroken chain of human intention, investment, and expertise. When that chain began to corrode, so too did the physical structures it was meant to preserve. The decline was not a singular event, but a slow, creeping entropy, a gradual silencing of a once omnipresent pulse. It began, imperceptibly, within the channels themselves. The very water that gave the city's life also carried the seeds of the system's eventual occlusion. Every aqueduct, drawing from springs rich in dissolved minerals, was a conduit for calcium carbonate. Over years, decades, and centuries, this mineral content precipitated out of the water, accreting onto the inner surfaces of the specus, the covered channel. This deposit, known as sinter, formed in hard, laminar layers, a kind of geological process in miniature. In the system's prime, its management was a routine, if laborious, aspect of maintenance. Teams of aquarii, specialized water workers, would periodically isolate sections of an aqueduct, divert the flow, and enter the channels. Armed with hammers and chisels, they would painstakingly chip away the stone-like accumulation, restoring the channel to its optimal dimensions and ensuring the designed flow rate, or modulus, was maintained. This was a constant, generational battle against the water's own nature. But as the late empire faced multiplying crises, the resources for such preventative maintenance dwindled. The central administrative power, which had once overseen these vital public works, began to fracture. The currency was debased, taxation became sporadic and predatory, and state priorities shifted decisively from civic infrastructure to the immediate, desperate needs of military defense. A legionary's salary on the Rhine or the Danube took precedence over the wages of an Aquarius in Hispania or Gaul. The knowledge itself, the specialized engineering skill passed down through guilds and apprenticeships, began to erode. As experienced overseers died or were pulled into other roles, they were replaced by less competent administrators, or not replaced at all. Consequently, the center was allowed to accumulate. A channel designed to be 1 meter wide might, over a century of neglect, be reduced to a constricted passage of only half a meter. The volume of water reaching the city would diminish, a slow and silent strangulation. Fountains that once projected water high into the air would be reduced to a sad trickle. The great public baths, the thermae, which required a colossal and constant supply, would have their hours of operation reduced or certain pools closed entirely. The effect was not immediate catastrophe, but a gradual degradation of urban life, a slow retreat from the hydraulic abundance that had defined the Roman city. Parallel to this internal choking was the decay of the external structure. Roman concrete, opus caementitium, was a marvel of durability, but it was not eternal. The constant presence of water, the very substance it was built to contain, was also a source of its undoing. Small hairline fissures, born of seismic tremors or simple settling over centuries, would allow water to seep into the core of the piers and arches. In the northern provinces, this was particularly destructive. The relentless cycle of freezing and thawing, winter after winter, would see this trapped moisture expand into ice, exerting immense pressure from within the structure, widening the cracks, spalling the facing stones, and slowly turning solid masonry into friable rubble. Vegetation, too, was a patient and insidious enemy. We now turn our attention from the past to the present, exploring the long, deep channels of influence that Roman aqueduct engineering has carved into the landscape of modern civil engineering. The stones of the Pont du Gard and the buried conduits of Rome are not merely relics of a bygone era. They are the foundational strata upon which much of our contemporary infrastructure is built. This is the legacy of the flow, a series of profound echoes that resonate in the concrete, steel, and computational models of today. The most fundamental principle, and perhaps the most elegant in its simplicity, is that of gravity flow. The Roman engineer, or architectus, understood with absolute clarity that water, if given a path, will seek its lowest point. The entire design of an aqueduct system, stretching for dozens of kilometers, was a testament to this single, immutable law of physics. The challenge was not in forcing the water, but in persuading it. This was achieved through the meticulous establishment of a constant, gentle gradient. The Roman surveyor, using an instrument known as the carbonate, a long wooden plank with a water-level channel carved into its top, would painstakingly measure the slope of the land. The goal was to maintain a gradient that was steep enough to ensure continuous movement and prevent stagnation, yet shallow enough to avoid excessive velocity, which could scour the channel lining and introduce destructive turbulence. Typically, this gradient was exceptionally slight, often in the range of 1 to 3 meters of drop for every kilometer of length, a ratio of approximately 1 in 3,000. This precise, almost imperceptible declivity is a direct conceptual ancestor to the design of modern open-channel systems. Our vast sanitation networks, the storm drains that lie beneath our city streets, and the great irrigation canals that turn arid land to fertile plains all operate on this identical Roman precept. While modern engineers employ laser transits and GPS for a degree of accuracy unimaginable to their Roman counterparts, the fundamental goal, the establishment of a continuous, predictable, and gentle downslope, remains an identical exercise in applied physics. The very material of the aqueduct speaks to a modern dialect of engineering. The Romans perfected a hydraulic concrete, opus caementicium, that was revolutionary. It was a composite material, made from a mortar of lime and a specific volcanic ash known as pozzolana, mixed with an aggregate of rubble or stone. The genius of this mixture was the chemical reaction of the pozzolana with the calcium hydroxide in the lime mortar. In the presence of water, it formed a calcium aluminosilicate hydrate compound, creating a robust, insoluble, and remarkably durable matrix. This concrete could not only withstand constant contact with water, but could actually cure and harden while submerged. This property was essential for constructing bridge piers in the middle of riverbeds and for lining the water channels, the specis, to make them impermeable. When we examine a modern dam, a concrete seawall, or a bridge foundation, we are looking at the direct descendant of opus caementicium. Today's Portland cement-based concrete is stronger and more standardized, but the fundamental concept of a hydraulic cement mixed with an aggregate to create a versatile, formable building material is a direct Roman inheritance. Modern research, in fact, looks back to Roman concrete, studying its unique crystalline structures that allowed it to self-heal small cracks over centuries, a quality we strive to replicate in our own advanced construction materials. The structural form most associated with the aqueducts is, of course, the arch. The Romans did not invent the arch, but they were the first to understand its full potential and to deploy it on a monumental scale. And so, the ancient stones fall silent, their long work complete. The great flow of an empire settles into a gentle echo in history. Thank you for joining us here at The Whispered Lore. Now, let the steady, quiet current of your own thoughts carry you toward peaceful sleep. May your mind be as calm as a still reservoir at dusk. Rest well. Good night.